So let me start with an apology to those of you who were expecting yesterday's talk to end after 1 hour instead of 90 minutes. Unfortunately, I was the only person who was not expecting that, since there was a schedule change that somehow eluded me. So the second portion of my course is on super-rigidity and obstruction bundles. Which won't be the entire talk today. I'll also go into something else at the end of today's talk, and then in this afternoon's talk and tomorrow, I will say more about the proof of a particular theorem, which I'm about to state. So first, let's recall the definition from yesterday. I have a simple J-Holomorphic curve V in a symplectic manifold M with almost complex structure J. So let's assume V is simple, meaning it's not a multiple cover, and index 0. So it lives in a moduli space with virtual dimension 0. We say this is super rigid if it's immersed. That's the easy part. And the hard part is that there's a dimensional condition on the linearized Cauchy-Riemann operators for all of its branched covers. Specifically, the following bound is always true. Dimension of the kernel of the linearized operator at J and V of phi. So phi is going to be some branched cover. This dimension is always greater than or equal to 2 times the algebraic count of branch points of the cover phi. And the condition I want is that this bound achieves equality for all holomorphic branched covers phi. So I didn't state it in exactly this way yesterday, but let me note why this is equivalent. I claim that this greater than or equal to always holds. And the reason for that is something that I observed yesterday, namely, if you look at the moduli space of holomorphic curves in the vicinity of a given branched cover, it always contains a smooth family of curves that have precisely this dimension. Namely, you just keep V fixed and let phi move through the moduli space of branched covers. I feel like this is a little bit too close to my mouth. Does it sound? Well, it sounds about the same. Maybe that's a little bit better. Okay? So there's always that smooth family of curves there, and the linearization of the nonlinear Cauchy-Riemann operator picks that up and sees a space of that dimension in the kernel. In general, there might also be more in the kernel, and there might also be more nearby curves than just the other branched covers nearby. Okay? So the super-rigidity condition is that at the linearized level, there is nothing more than that. And that has several nice consequences. That's sort of, you're used to the implicit function theorem or the inverse function theorem saying like something, in the inverse function theorem, if you have a smooth nonlinear map and you look at its linearization and find out it's an isomorphism, then that forces the nonlinear map to also be a diffeomorphism in a nearby neighborhood. So we get a similar result here. Well, I'll state the corollary in a moment. Let me first tell you that this condition can actually be achieved, and this is a relatively recent theorem. We'll call Theorem A. So if the dimension of our symplectic manifold is at least 6, then for generic J compatible with omega, all simple index 0 J-holomorphic curves are super rigid. So I'm going to spend a lot of effort in the last two talks of this series explaining why that and various related things are true. Let me say first what follows from it. So we talked yesterday about this setting of symplectic Calabi-Yau threefolds, where all holomorphic curves have index 0. So the virtual dimension of every moduli space is 0, but we've seen, of course, that when branched covers exist, the actual moduli space of holomorphic curves will have a positive dimension, or at least is not guaranteed to be anything as nice as an orbifold of dimension 0. What we can say now for generic J in a Calabi-Yau threefold, for all integers g greater than or equal to 0 and homology classes A in H2 of M, there exist at most finitely many simple J-Holomorphic curves of genus G with homology class A, and they're all embedded and disjoint. All right, so there's a hard part and an easy part of this statement. The easy part is embedded and disjoint. If we're in dimension at least 6, then one can show pretty easily that generically an index 0 J-holomorphic curve will always be embedded, and any two index 0 curves, they're isolated objects in the moduli space, any two of them will generically be disjoint. There's enough room to move around in 6 dimensions to make sure that that's true. The hard part is the statement that there are only finitely many of them. And in general, that's not something you would expect to be true because, well, let me tell you what specifically you have to rule out. Now, this is not going to be every detail of the proof, but just the main portion. Let's say mg star of aj, I will use this to mean the set of all simple curves in the moduli space mg aj. So this, we can at least say, is a smooth zero-dimensional manifold, since we're assuming the curves are simple, and therefore they are regular for generic J. So this is a discrete set, but it might be infinite. You have to show that it's compact. So with compactness, there's always the danger that you could have a sequence of curves converging to something that's no longer a smooth holomorphic curve, but is a nodal curve. In this situation, it's not so hard to rule that out because we can show generically that any two holomorphic curves, if they're simple, don't intersect each other. So there's very few ways you can actually construct a nodal holomorphic curve. The real danger is that you could have a sequence of curves converging to a multiple cover of some other curve, something that's no longer in the space M star. So that's the main danger. Let's say we have a non-compact sequence UK in this space such that UK converges to U infinity, which is a multiple cover, V of phi, something non-simple. Well, if that's true, we've assumed V is super rigid. And that has certain consequences. Super-rigidity says when you linearize the Cauchy-Riemann operator at this multiple cover, its kernel is only seeing enough dimensions to include the stuff that you get by perturbing the branched cover in its own moduli space. And it doesn't see anything else. Right? So the implicit function theorem then tells you all J-Holomorphic curves in some small neighborhood of V of phi are of the form V of phi prime for some other branched cover phi prime. So they're not simple. And that's a contradiction, because we assumed that these simple curves UK are converging to this. So that's the main idea. One has to do a little bit more than that, because you have to also rule out the possibility that this sequence is converging to a nodal curve whose components all consist of branched covers of the same simple curve. Okay? So I'm not going to go into these details, but this is the seed of the main idea that you need to rule that out as well. Okay. Yeah. Why is, sorry? That was the assumption, right? Well, it's a corollary of Theorem A. Theorem A says that this is going to be true for all simple curves for generic J. Say again? Phi is a branched cover. V is assumed to be a simple curve. Yeah. So you can always do that, right? Any holomorphic curve factors into the composition of some simple curve with a holomorphic branched cover of Riemann surfaces. Let's try that for a while. Okay. So in this Calabi-Yau setting, the Gromov-Witten invariant, we've got to take 0 marked points because all the holomorphic curves have index 0. If the moduli space has virtual dimension 0, you don't want to apply any constraints. You just want to count things. So this invariant, strictly speaking, it's a homomorphism from the m-fold tensor product of the cohomology to the rational numbers. Well, m is 0 here, the 0-fold tensor product. That just means what we have is a rational number. So this invariant is supposed to be, well, literally, by my definition from yesterday, it's a count of elements of this compactified moduli space mg bar aj nu, where nu is some generic inhomogeneous perturbation of the Cauchy-Riemann equation. And so you count solutions to that perturbed equation, and you get a rational number due to symmetries that are built into the picture, which I'm not going to discuss. This is for generic u, nu rather. So at the moment, there's another count I can imagine defining, because I just learned that this moduli space of just plain simple index 0 curves is finite. I could count them. And it's natural to wonder, does that also define some kind of invariant? If it does, how is that related to the Gromov-Witten invariant down here? The answer is no. And the reason for it is that super-rigidity can fail under deformations. So there's various phenomena that can arise out of that failure. I'll just give you one example. There exist these so-called degree doubling bifurcations. So this is a phenomenon that was observed. I always forget if this is 1995 or 96, but there was a paper by Taubes. This is it. Have I done anything differently? We'll see. So, there was a paper by Taubes in which he defined the so-called Gromov invariant, which is something like the Gromov-Witten invariance that counts holomorphic curves, but specifically in symplectic 4 manifolds. The point for Taubes was that it's isomorphic to the Seiberg-Witten invariant for symplectic 4 manifolds. Now, this invariant is an invariant because, well, he defines a specific way of counting both embedded curves and certain multiple covers. And it's a rather complicated formula. In particular, how to count the multiple covers is a bit tricky. It has to be exactly the way it is because under generic deformations of the data, various things can change, and you have to make sure that your count doesn't change. So one of the things that can change is if I imagine taking a homotopy of almost complex structures from J0 to J1. So here's my parameter S, and I'm going to draw a picture of the moduli space, parametric moduli space, dependent on this parameterized family of J's. Okay, for this I need color. So let's imagine the following scenario. All of our simple curves have index 0, so they're isolated objects for each individual j. But when you let j vary in a one-parameter family, you get one-parameter families of elements in this parametric moduli space. So you have a one-manifold, and it can sometimes turn around like this. So this phenomenon here is a birth-death bifurcation. As you move time forward from J0 toward J1, you see two holomorphic curves that at some point come together and they annihilate each other. You have to make sure, of course, that when you count them, one of them gets a plus sign, the other gets a minus sign. So they add up to the same number that you count over here. That's relatively straightforward. This is not the interesting phenomenon. The interesting phenomenon is this one. So let's say these are all simple curves. Let's say these are all double covers. And it's a nice, well-behaved family of double covers in that the underlying simple curves are regular the whole time, which is why they're just deforming smoothly as you move from one side to the other. So, say u equals v of phi. What can, however, go wrong is you have a point somewhere, some bad parameter value, for which super-rigidity fails. You haven't seen this happening in the picture yet because I just drew the simple curves with their double covers over them. Right? And say I should also add that they're unbranched double covers in this example. So unbranched means that the moduli space of branched covers itself is zero-dimensional. There's an isolated covering map of Riemann surfaces for each parameter. So you just have this nice smooth family of double covers moving along, but super-rigidity fails for one of them in particular, which means that all the others are Fredholm regular, but this one is not. So right here, the implicit function theorem is no longer giving us a really accurate description of the moduli space in a neighborhood. We're missing something, and what we're missing, Taubes discovered, is that a family of simple curves can just spring right out of this that wasn't there before. So this is another one-parameter family of simple curves. It exists after the bifurcation, wasn't there before it. Okay? So these simple curves, if you move back here, they all converge to this double cover. So in this particular homology class, we're assuming that the double covers here have the same homology class as these simple curves also do. There's always a danger right? This homology class, therefore, is the double of some other homology class. So there's a danger that some family of simple curves could converge to a double cover. When super-rigidity fails, it can actually happen, and it does happen. So that's the degree doubling bifurcation, and what you see is from here until that bifurcation happens, the number of elements counted with signs in this moduli space of simple curves equals 0, but after it happens, that number is either plus or minus 1, depending on which sign counts these simple curves. So this tells you just counting simple curves will never give you an invariant. So Taubes figured out what to do about this in defining the Gromov invariant by determining exactly how these double covers need to be counted. So you can kind of guess the answer if you think about it a little bit from this scenario. Since they're double covers, the right thing to do when you count is divide by the order of the automorphism group. So you're dividing by 2. Each of these curves needs to be counted as plus or minus 1/2. So for instance, if this counts as 1/2, this one is 1, this one is minus 1, you get a total count of 1/2. What's going to happen over here, now this is counting for 1. That means as you went through the bifurcation, you have to change the sign of the 1/2. This becomes minus 1/2. That's essentially what happens, up to a sign. It's useful to think of the moduli space as an orbifold. I mean, you need more than that. You need to think. Yeah. So, I mean, yeah, but my problem with just saying it's an orbifold is that in the neighborhood of this point, the parametric moduli space is not an orbifold. It's not smooth, right? It's some sort of branched manifold or branched orbifold. So you have to have a precise picture of what that branching is, and that's what's required. So at the moment, that's just a warning about what you shouldn't do, but I'll say some more about bifurcation theory, hopefully, if I have time toward the end of this mini course. What I want to say now is what the count of finitely many simple curves actually does have to do with the Gromov-Witten invariant. Yeah. Mm-hmm.
This actual count of curves is not, for J0 and J1, their actual count would be, even if J0, for J0 and J1, there is, everything is.
Yeah, the count, if you're just counting the simple curves, then that count will be different. Yeah. It is something that you could prevent from happening if you could show that super-rigidity holds for every JS in this family. But if there's one parameter where it fails, then something like this can happen. Okay. So, yeah, one of the things I do want to try and explain is why super-rigidity can indeed fail and exactly how it fails when it does. But first, let's talk about multiple cover contributions. So one of the things we can do if we have the super-rigidity hypothesis is the following. Say U is a super-rigid curve. I define n, d, g of U. This is notation from the Gromov-Witten theory literature. It's more favored by algebraic geometers from what I've seen. This is some rational number, which we define to be the count of solutions to the equation d bar j u prime equals nu for some generic small perturbation nu, such that u prime is a small perturbation of u composed with a branched cover phi, some branched cover phi. Okay? Why is this well defined? Well, we established that the space of all branched covers of a single simple super-rigid curve U is actually an open and closed subset of the larger moduli space. It's a component of the moduli space. You don't have other elements of this moduli space nearby that aren't of this form. So if you think of it, take a small neighborhood of this family that is an open subset of the moduli space, but only containing that family of branched covers. Now, turn on your perturbation just a little bit so that you can actually start counting solutions to this equation because they're all regular. Now, you're going to have some number of solutions to this equation in a neighborhood of the original family of branched covers. It's going to be some finite set that you can count with signs, and also dividing by isotropy groups so you get a rational count. But you don't know how many there's going to be as such. It's a well-defined count. Okay, and I'll actually give you a formula for it. So the whole notion of being a multiple cover disappears once you turn on the perturbation. So you have these solutions that are in a neighborhood of this family of solutions to the unperturbed equation. This is supposed to be the count of those. Sorry? We're considering it for all possible phis. Right? So this is, instead of some, let's say any. Right? In other words, fix some very, very small neighborhood of the whole family of all the branched covers of U. This is a count of the set of solutions to this equation that exist in that neighborhood, in the space of maps. Okay. So, one quick note about this. You can even do this in the case where the degree of the cover, I should have said d-fold branched cover. That's part of the definition. That's what this d means in the notation. Right? You can do that also when d equals 1. Now, when d equals 1, a branched cover, the only possible one is the identity map. So what you're actually counting then is solutions to this perturbed equation, which are sufficiently close to the original simple curve. There's going to be exactly one of them if the original curve, right? Super rigidity for the original curve just means the original curve is regular. So it's going to perturb by the implicit function theorem. You get one, you count it with a plus or minus sign. So we note n1 g of u equals plus or minus 1 if u has genus G. On the other hand, you can also define this with different values of the genus up here, in which case what you have is something more complicated. Let's not worry about that right now. Yeah. I mean count in the sense of a rational number that you have to get by defining this generic inhomogeneous perturbation that depends on something in a lift of the Dulin-Mumford space, so that you have to divide the answer in the end by the degree of this cover. Yeah. All right. So there's a theorem which is mainly due to Alexei Jinger that tells you how to actually compute these multiple cover contributions. We'll say if U with domain sigma prime is super-rigid, then there exists a vector, actually not strictly a vector bundle, but an Orbi bundle, ob, over the compactified moduli space of branched covers of genus G, whose fiber at a given branched cover phi is the co-kernel of the linearized Cauchy-Riemann operator at U of phi. And the multiple cover contribution, NdG of U, is then, so I'm going to write it first in this informal way, which I'll have to explain a little bit what it means. I'll put quotation marks around it. Integral over the virtual fundamental class of the space of branched covers of the Euler class of the obstruction bundle. Okay. So if you're an algebraic geometer, then maybe you're perfectly happy with virtual fundamental classes. I personally am not. So I'm going to also express this in an alternative way. A virtual fundamental class is basically a way of taking this compactified moduli space of branched covers, which might not actually be such a nice object globally as you'd hope, and pretending that it's a closed manifold or orbifold at worst, so that you can assign it something like a fundamental class. Well, another way that you can change this thing into an actual closed manifold is to introduce an inhomogeneous perturbation to the Cauchy-Riemann equation describing holomorphic maps from a Riemann surface to another one. So another way you can then say this is, for me, this is a definition. Say it's the number of zeros of a generic section of the obstruction bundle ob over a slightly perturbed base mg so homology class D times the fundamental class of sigma prime, complex structure J prime, and also an inhomogeneous perturbation nu prime. So for some generic small inhomogeneous perturbation nu prime. So maybe let's not worry about this extra inhomogeneous perturbation. Let's not worry about the virtual fundamental class. Let's just focus on the case where this compactified moduli space of branched covers is a relatively nice object. What we're just saying is there is some vector bundle, this obstruction bundle, whose Euler class over that space of branched covers computes the multiple cover contributions we're interested in. So now if you combine that result with the previous one that I stated about finitely many simple curves, you get a formula to compute the Gromov-Witten invariants. Yeah. In practice, yes, there is some specific section, but it doesn't matter since we know we can compute an Euler number by just choosing anyone. I'll tell you. Yeah. So, corollary when combined with theorem A is that for generic J in a Calabi-Yau threefold, for all genus G and homology class is A, there exists a finite collection of disjoint embedded curves UI of genera GI, which will always be less than or equal to G, and homology class satisfying some natural number DI times homology class of UI equals A for some DI in the natural numbers, such that the Gromov-Witten invariant is just the sum of the multiple cover contributions of these guys for degree DI, genus G, the UIs. So this is what I mean when I say that the Gromov-Witten invariants localize. There is some finite set of embedded curves that are all disjoint, such that the Gromov-Witten invariant of your Calabi-Yau depends only on what's going on in an arbitrarily small neighborhood of those curves, determined by these multiple cover contributions. Okay, so let me go back a bit and explain the geometric idea behind this obstruction bundle. Why does computing the Euler number of this obstruction bundle determine the multiple cover contribution for you? I want to not explain that directly, but give you sort of the finite dimensional analog. The geometric idea is the same, but maybe you can get your hands on it a little bit more easily. So we'll talk about obstruction bundles. Sorry? No, I think I really mean NG, because I'm trying to compute the contribution to the genus G Gromov-Witten invariant. UI has a different genus in general. That information is contained in UI. Yes, did I say? I certainly meant to say. Oh, I didn't say. No wonder. Okay, so here's my definition of multiple cover contributions. So the number is the number of solutions to this perturbed equation for some generic small perturbation such that the solution is a small perturbation of U of phi, where phi is any d-fold branched cover of genus G. There we go. That's what I should have said. Okay, because in general, depending on the number of branch points, you could have d-fold branched covers with various genera. So we're looking at one in particular. So in finite dimensions, I want to think about the finite dimensional analog of holomorphic curves of index 0. So that's a Fredholm problem given by some section of a vector bundle. It's an infinite dimensional vector bundle normally, whose linearization is always an index 0 Fredholm operator. So the finite dimensional analog of this is that I have a vector bundle E over B, a real vector bundle with rank equal to the dimension of the base. So that will make sure that linearizations of sections are also index 0 Fredholm operators. And then S will be a section, say smooth. Now, of course, we'll call an element of its zero set regular if one way to say it is X is a transverse intersection of S with the zero section. That's equivalent to saying that the linearization of that section at that point as a linear map from the tangent space to be to the fiber over that same point is an isomorphism. Right, so this is what makes S a Fredholm section of index 0. Now I want to consider cases where my zero set is not regular. Yes, Janko. Yeah, it is Fredholm, but it's not always index 0. Okay, I said this in the wrong order, yes. Okay. I should have said this back here before I talked about regularity. Indeed. So let's consider a compact subset M in the zero set, where the zeros are not all regular. But let's say that this compact subset M is a closed manifold. Well, we'll say in particular this subset M is a clean intersection of S with the zero section if M is a smooth submanifold whose dimension is exactly what you would predict if you'd compute the kernel of the linearization of S. In other words, dimension of M equals the dimension of the kernel of the linearization ds at x for all x in that subset. So hopefully you can see the relationship between this and my super-rigidity condition. Right? The super-rigidity condition is a kind of clean intersection condition where you have a positive dimensional family of solutions of an index 0 Fredholm problem. So they cannot be regular. But you have the next best thing, which is that the kernel of your linearization has dimension equal to exactly the dimension of that family of solutions. Yeah. Indeed. So yeah, that's another way of saying it, that the tangent space to this family, so but first condition is that the family is a manifold. Second is that its tangent space at each point equals precisely this kernel. So I'm not there yet. I'm about to say. So there's two facts you can now deduce from the implicit function theorem under this condition. First is that M is an open and closed subset of the zero set, S inverse of 0. And secondly, there exists a smooth vector bundle I'll call ob over M, whose fibers ob at x are the co-kernel of that linearized section. So let's observe now. The linearization has index 0, so its co-kernel has the same dimension as its kernel, which is the dimension of M. So that means the rank of the obstruction bundle is also, again, exactly equal to the dimension of the family of solutions. All right, so the main thing I want to say is the following proposition. Given an open neighborhood of M, called a neighborhood U, sitting in the base of the bundle, with the property that the intersection of this neighborhood with the zero set of the section is exactly M. We can now say for any sufficiently small perturbation, or let's just say sufficiently small section mu of our bundle, with the property that our original section plus this extra one is transverse to the zero section. Now I can count the number of points in the zero set of this perturbed section, just restricted to that neighborhood. So take S plus nu, restricted to that neighborhood U, count the number of zeros we have in that neighborhood. Sorry? Yes, I do. Thank you. Sufficiently small. It's not that you can't read. You can't read what I haven't written. Right. So the number of solutions we have in this neighborhood after the perturbation will be exactly equal to the Euler number of the obstruction bundle. Right. So, and indeed, as Ritwik asked, it will turn out to be equal to the precise count of zeros of a specific section of that bundle once I set this up the right way. So we'll see this in the proof. So first step, let's choose a splitting of our bundle. We know, of course, that over M, over this subset of the zero set, there's a splitting of each fiber into the image of our linearized section plus something else. You can choose the orthogonal complement of the other thing with respect to some metric. Let's extend that to our small neighborhood. So choose a splitting of E restricted to this neighborhood into I plus C, such that for all points x on our manifold M, the fiber of Ix is just the image of the linearized section. Thus, Cx is now going to be the co-kernel of that linearized section. And let's denote by pi I the projection from that bundle to the I factor. So what I can observe now is we can define a section of just this subbundle I over that neighborhood. And that is transverse to the zero section. By construction, that's transverse to the zero section of I. Right? Because that's just the statement that the linearization at each point of this section is a surjective linear map. That linearization is this linear projection composed with the original linearization for all x in M. Okay? Which is actually, I can remove pi I from that, because by definition, this is the projection to the image of this second linear map here. So we get the same thing if I remove pi I from the picture. But now it's surjective. So another observation is that now the kernel of the linearization of this modified section is, of course, the same as the original kernel, which has the same dimension as M. So now imagine what happens if you add your small perturbation to this section, but then take its projection. So for, let's say, S prime is the perturbed section S plus nu with any sufficiently small nu composing pi I with this modified section S prime, you get something that's also transverse to the zero section. And let's call M prime the zero set of this projected modified section. So that's some subset of U, but it's also going to be a smooth manifold, compact, smooth submanifold, which is some small perturbation close to M. So the other thing I wanted to observe, I made this observation about the kernel of the linearized operator, but I didn't tell you why. So note, since that kernel has the same dimension as M, what I want to observe about this is that after possibly shrinking U to a smaller neighborhood, the zero set of this projected section equals precisely M. In other words, there's going to be no other point in that small neighborhood of M with the property that the projected section at that point is zero. Right? We already know that the section itself is not zero at any point in that neighborhood, but the projection also won't be. That's due to this dimensional condition using the implicit function theorem. So I made this small perturbation of M to M prime by projecting the section and then perturbing the section a little bit, which I could do because it intersects the zero section transversely after I've projected it. So now, for x in this neighborhood, my perturbed section, S prime, will be 0 if and only if both its projection to the I factor is 0 and its projection to the C factor is 0. So the first condition means x has to belong to M prime, that modified manifold. And the second condition is that x belongs to the zero set of some other section, sigma. This is the so-called obstruction section. So sigma is defined from M prime to C, and its definition is very simple. It just sends the point x to S prime of x. Why is that a section of C over M prime? Just because being in M prime means the projection to I already vanishes, right? So projection to I vanishes, the same thing as saying that S prime of x is in the subbundle C. So that's a section of our subbundle C, which is actually just a small perturbation of the original obstruction bundle. We have number of zeros of sigma is the Euler number of the subbundle C restricted to M prime. Now M prime is just a small perturbation of M, so this is the same as the Euler number of C restricted to M, and C restricted to M is precisely the obstruction bundle. So there we go. Right, that's as much as I want to say about the obstruction bundle. This was just the finite dimensional case, but I only chose the finite dimensional case for cosmetic reasons, so that you can feel you can picture it a little bit better. What you have to do in the infinite dimensional setting of Gromov-Witten theory is really exactly the same thing. Sorry? Yeah, the point is, of course, is kernels and co-kernels are finite dimensional. Right? I mean, the only difference is that in the general case, you can't assume that this bundle E over B is finite dimensional. That's going to be infinite dimensional. But the rest of the discussion is the same. All right, so this morning, Sushmita was telling me that no one at this workshop has yet really talked about transversality, so I'm going to talk a lot about transversality. One of my main goals for the rest will be to prove what I stated as Theorem A, this statement that super-rigidity generically holds. But first, I need to cover some more classical things in the background, just to make sure that we sort of have these ideas in our head. So I want to discuss transversality for simple curves via the Sartre-Smale theorem. And this is one of these classical topics that you can read in all of the books on the subject, especially Macduff and Zolomon, or whatever else. I need to recall how it works because it contains a bunch of ideas that I'm going to reuse. So first, let's write the theorem again. For J generic, all simple curves in this moduli space M of J are regular. So here's the idea of the proof. I have to first make a choice of a nice space of perturbed, almost complex structures. So what I'm going to say in general is that J, this is curly J, denotes some Banach manifold of perturbations of a fixed, almost complex structure J naught. So there's various ways that one can set this up. I have a personal favorite way, but it's not the only way. My personal favorite is the trick introduced by Fleur in one of his original papers on Fleur homology in the late 80s. We can say J is the following set of almost complex structures. Let's define them as small perturbations of J naught using some exponential map within the space of complex structures on each tangent space. So I don't need to write down precisely what the exponential map is. Let's just write exp at J naught of y for y, an element of the tangent space to J naught in the space of almost complex structures. Just thinking of that, I just really mean, first of all, as a smooth section of some vector bundle that describes perturbations within the space of almost complex structures. But now I need to add conditions to make this, to give this a Banach space structure, or Banach manifold structure. It's going to be a Banach manifold with exactly one chart, identifying it with an open subset of a Banach space. And those conditions are, first, let's just make sure that this y is not too large for things to get out of control, meaning too large in the C0 norm. So let's say the C0 norm of y is less than epsilon for some epsilon. And more importantly, to define a Banach space norm, we can say the sum for k going from 0 to infinity of some numbers epsilon k times the ck norm of y is less than infinity. So this is for some fixed sequence of positive numbers epsilon k converging downward to 0. Right. So that was Fleur's trick, the so-called C epsilon space. One has to check a few things, namely that there actually is a Banach space with a norm defined by this kind of formula, and that if you choose the sequence of epsilons to converge sufficiently fast to 0, then that Banach space actually has a lot of things in it, such as smooth bump functions with arbitrarily small support. That's something you need for the applications. Anyway, one can check these things, and you get a separable Banach space. And call this a Banach manifold with one chart. Now I use this to define a so-called universal moduli space. It? Why does it? No, it's an open subset of a Banach space. So, the universal moduli space I'll denote by M star. It's the set of all pairs J and U, where J belongs to this Banach manifold of perturbed almost complex structures, and U is then an element of the moduli space of specifically J-Holomorphic curves for that particular J. And also I require U to be simple. That's going to be necessary for the main thing I want to prove about the universal moduli space. There's a natural projection from this space to this space of almost complex structures, which I'll denote by pi. It sends the pair Ju to just J. So one basic observation about that projection is it's a Fredholm map. In other words, the linearization, the derivative of that map is a Fredholm operator from the tangent space to the universal moduli space to tangent space to J. At all points in the universal moduli space. Right, that's just, once you've assured yourself that the universal moduli space is a smooth manifold. So let's actually add that. If M star is a smooth Banach manifold, because we haven't proved it yet, okay, then it's just a bit of linear algebra to convince yourself that this derivative will always be a Fredholm operator, because you can relate that to the derivative of the Cauchy-Riemann operator that cuts out each of the individual moduli spaces for you. And that one is definitely a Fredholm operator. So for smooth Fredholm maps, there's an infinite dimensional generalization of Sard's theorem that's due to Smale. Actually, before saying that, let me add one word. Not smooth Banach manifold, but smooth separable Banach manifold. The technical condition is needed for Smale's theorem. So, under these conditions, the Sard-Smale theorem tells you that generic J in the target of that projection are regular values of the projection, which of course means that this moduli space M star J of all simple curves that are J-holomorphic, that's just pi inverse of J. That is a smooth manifold whose elements are all regular. Okay, so up to various minor details, such as the fact that my space of perturbed almost complex structures is a little bit weird. It's not exactly the same thing as all C infinity almost complex structures near J naught. Right? That's something we'll have to fix at a later stage. But other than things like that, and the fact that M star is a smooth separable Banach manifold, then this finishes the job. Right? The main step is really to show that M star really is a smooth separable Banach manifold, because only then can you apply the Schwarzschild theorem. So let's sketch why that's true. So locally, M star looks like the zero set of something. For a section D bar that's now taking J times our original Banach manifold to some slightly modified or extended Banach space bundle E prime. Namely, this just takes a pair. So B consists of pairs little j with U, and curly j is big J, so this takes it to D bar j of U as before. So remember, that's Tu plus j of Tu of little j. So I can linearize that smooth section and it turns out I don't need all of its partial derivatives with respect to each variable. I just need it with respect to j and u. So let's write it this way. We linearize in the direction of y, 0, eta. So we're not perturbing the domain complex structure, but just the other two pieces of data. So if you perturb j in direction of y, it just changes this second term, j of Tu of little j. You get y of Tu of little j. And if you perturb u in the direction of eta, that's some vector field along u, well, let's just write that down as d sub u of eta. D sub u is a fairly well-known object, which I think was presented at some point earlier in this workshop. It's a differential operator from the space of sections of the pullback bundle U star Tm to the space of 0, 1 forms on sigma valued in U star Tm. That's the so-called linearized Cauchy-Riemann operator at U. So specifically, you can write it down by the formula du of eta equals some covariant derivative of eta plus j of covariant derivative of eta of little j plus something you get by also differentiating the almost complex structure in the direction of eta. This is for any symmetric connection del on M. Let's introduce a bit of shorthand notation and call. So this operator that sends y and eta to this thing over here, I'm going to call L of y eta, the main lemma I need to prove. Is that this operator L, now in the suitable Banach-based context, so let's say taking the tangent space to J in the space of almost complex structures, plus not just the set of all smooth vector fields along U, but we need to choose a suitable Sobolev space. Let's say W1P sections of the pullback bundle U star Tm, mapping to the Banach space LP sections of Hom bar, so it's a bundle of antilinear maps from T sigma to U star Tm. This is surjective. So this is what will tell you by the implicit function theorem that the universal moduli space really is a smooth Banach manifold, because locally, right, this is the linearization, or at least it's part of the linearization of a section whose zero set is that universal moduli space. Okay. Was there a question? Okay, so why is that operator surjective always? First observation, the linearized Cauchy-Riemann operator is Fredholm, so its image is closed. Actually, that implies also that the operator we're talking about, this L, oh, sorry, I don't want to say that. In any case, its image is closed. That implies that the image of L is also closed. So if you want to show that the image of L is everything and you know that it's closed, the Hahn-Banach theorem kind of tells you what to do. By Hahn-Banach, if L is not surjective, then there is some non-trivial element in the dual space of the target which annihilates all of its image. In other words, there exists some element lambda which is non-zero living in the dual space of that target space LP. Let's actually rewrite that dual space using the Riesz representation theorem. So that's LQ for 1 over P plus 1 over Q equals 1, such that it annihilates everything in the image. That means after picking some bundle metrics so you can define an L2 pairing, L of y eta paired with lambda in L2 equals 0 for all y eta. That's actually two conditions, because you can plug in arbitrary values of y and eta, so you get the two conditions. First, y of tu of j paired with lambda is 0 for all y in this tangent space to the space of almost complex structures. And second, du of eta paired with lambda is 0 for all eta in this space of W1P vector fields along U. Now, the second condition in particular is true for all the smooth vector fields. And you can then interpret this as a some statement about an operator on lambda in the sense of distributions. So this is saying lambda is a weak solution. It has to be, in general, weak because right now I only know that it's in LQ. It might not even be continuous. But it's a weak solution to the formal adjoint equation. du star of lambda equals 0. Du star is another first-order differential operator that you can derive from that formula for du over there, and you can show that it's also a Cauchy-Riemann type operator on some vector bundle. So, in particular, du star also Cauchy-Riemann type. So there are elliptic regularity results about this that tell you if it annihilates lambda, even just in the weak sense, then lambda is actually smooth, and du star equals lambda classically, or du star of lambda equals 0 classically. So that's one observation. Next one is that according to this first condition, lambda should be such that this pairing is 0 for any y I might choose. Now this is where I need to use the assumption that my holomorphic curve is simple. So if u is simple, then in particular it has what we call an injective point. There exists a point z0 in sigma at which the derivative of u does not vanish, and also there is no other point in the domain that u maps to the same point. Okay? If every point had the property that some other point also maps to the same point, then u would have to be a multiple cover. So such an injective point does exist. This means u inverse of u of z0 is just that set of one point, z0. So let's also observe the set of such points is clearly open. Okay, so now having chosen such a point, we can choose our perturbation of the almost complex structure y in the vicinity of the image of that point, u of z0, to make sure that this pairing just in the bundle metric is positive. Y of tu of j paired with lambda, not L2, but just this pairing equals 0 near z0. Okay. I don't know what lambda is, but whatever lambda is, sorry, I don't want it to be equal 0, I want it to be positive. So I have enough freedom in how to choose y so that I can make these two things equal up to a positive scaling in a neighborhood of that point. And I just need to be able to specify what y is near u of z0 in order to do that. And I don't have to worry about that changing. That has no effect on anything that's happening elsewhere on the domain of the curve, because only that one point is mapped into that neighborhood, or only a neighborhood of that point is mapped into that neighborhood. So I can make this choice near z0, but I can also assume that it vanishes elsewhere by making y have support in a neighborhood of this point, u of z0. And now I have a contradiction. Those two things can't both be true if this L2 pairing is 0. Oh, the only thing that would prevent me from doing this, I can say one is false, unless lambda vanishes in a neighborhood of z0. Okay? That's the only thing that could prevent me choosing this condition to be true. And if lambda happens to vanish at z0, right, the set of injective points is open, so I could just move z0 a little bit to somewhere where lambda doesn't vanish. The only thing that would prevent this is if lambda actually vanishes in an entire neighborhood of that point. So the final observation is that that cannot happen due to a unique continuation result. So I'll just write that down and stop for now. So I'm calling this, in generic terms, a unique continuation lemma. This follows from something called the similarity principle. But there are also other things like Ahrenstein's theorem that one can use to derive this. And one way of saying it is, if I have a first-order differential operator from the sections of some bundle E to the 0, 1 forms valued in E, so let's say this is a Cauchy-Riemann type operator on a complex vector bundle E over a Riemann surface sigma, and let's just make sure we all know what Cauchy-Riemann type means. It means it satisfies some kind of Leibniz rule. D of f times eta equals f times d eta plus d bar f times eta for all real valued smooth functions f and sections eta. Then for all non-trivial solutions to the equation d eta equals 0, eta cannot vanish to infinite order at any point. Okay? Vanishing to infinite order means you take its first derivative, it's 0. Having done that, the second derivative is well-defined, is also 0, and inductively so forth. Right? Or in any choice of local coordinates, its Taylor series vanishes at that point. So that's something, of course, we all know that it's true for holomorphic functions in complex analysis. It's also true for solutions of an arbitrary, even just real linear Cauchy-Riemann operator on a vector bundle due to the similarity principle. And it tells you in particular, eta cannot vanish on an open neighborhood unless it vanishes everywhere. So that's what gives you the contradiction at the end of this. Right? The reason I've been spending time on this is that most of these ideas will appear again when I try to explain the proof of super-rigidity and related results about transversality for multiple covers. So I'll continue with that in this afternoon's talk, but I'll stop here for now. Yeah. Say again.
What is the regularity of eta?
For the unique continuation lemma? Well, in the background of this, there's also elliptic regularity that tells you if eta satisfies that equation even weakly, and eta is at least LP for some p greater than 1, then eta is actually smooth. So you can... Yes, assume D has... Okay, I don't have to assume D has smooth coefficients. I can weaken that somewhat if I really try, but I'd have to look at it quite carefully. So yeah, it can be weakened somewhat.
I had one question. Maybe we'll about this later, but so initially that theorem you stated that for a generic J in a Calabi-Yau threefold, these NGs are finite, but that doesn't imply immediately that for a specific, say the quintic threefold, those numbers would be finite, right?
No, indeed. So in particular, you're not allowed to assume that J is integrable. In fact, when I prove that theorem, you'll see that the generic J's I'm giving you are guaranteed to be not integrable. So that's okay in some sense, because we know that super-rigidity is false for some Calabi-Yau threefolds in the algebraic category. There's a paper of Brian and Pandey that finds counterexamples. So it was never really expected that that result should hold in the complex category. It's really a symplectic property. It's true for generic J compatible with a symplectic form.